Hey everyone, so this week's lab is the Ideal Gas Law Remote Lab. Similar to last week, we're going to be starting off with some physics at home activities, and then with any time you have left over after that, you can do the simulation questions. The first physics at home activity is figuring out what the density of air is in your room or wherever you're at. The basic idea behind this one is you're going to be using the barometer in your phone to calculate a change in pressure between two heights. Or excuse me, not to calculate, but to measure what the change in pressure is between two heights. There are a couple of ways that you can get a pressure reading from your smartphone, but I would say the best thing is if you have an Android or an iPhone, you can go to the Physics Toolbox Sensor Suite and they have a built-in barometer there that's pretty easy to read off. So the idea here is you'll measure a pressure at two different heights and you'll make an estimation or a measurement as to how far those two heights are separated by. Then you'll be using Bernoulli's equation to figure out what the density of air is. And I'll show you what that looks like real quick. So Bernoulli's equation is P plus 1/2 rho, where rho is density, v squared, velocity squared. And so I guess to talk through each of these terms, P is pressure. This term is a kinetic energy term. So we have 1/2 density times velocity squared. And then again, we have a gravitational term, which is the density times the gravitational constant times the height. And so the idea here is if you make, I guess since this equation is equal to a constant, if you make two of these measurements, you know they're equal to each other. So you could have P1 plus 1/2 rho V1 squared plus rho g H1 equals P2 plus 1/2 rho V2 squared plus rho g H2. And so the approximation we're going to make to be able to get our calculation for what rho is, first off, is we're either going to say that the air is not moving, or we're going to say that the air is roughly moving at the same speed in both columns. So we can go ahead and forget about these kinetic energy terms. And then you just have P1 plus rho g H1 equals P2 plus rho g H2. And so now I would set the bottom floor height to 0 so you can forget about one of those height terms, or equivalently we can work in height differences rather than absolute heights. But any way you cut it, you'll end up with, on one side of the equation, delta P, so P2 minus P1, and then on the other side of the equation it'll be rho g delta H, so rho g times the change in those heights, and then you're just solving for rho. So you can go ahead and divide both sides by gh, that'll give you a figure for rho. And then you should be able to work through the rest of these calculations fairly easily. Next, you get a ratio of N over V using the ideal gas law, which is that PV equals nRT, so that's not too bad. You'll just have to rearrange a couple things. Take your density and divide by that to find the mass per mole ratio, and then you can calculate an ideal mass per mole ratio. This was another bit that a few people had questions about, but this isn't a bad calculation at all. So basically the way to think about this is you are composing 1 mole, and it's going to be broken down into these percentages with these substances. And then each of them has a molar mass in grams per mole that correspond with them. And so the way to calculate your ideal mass per mole is just to take this percentage, 78%, so I'd say like 0.78 times its molar mass, 28, and then go ahead and add up the next thing. So plus 0.21 times its molar mass, so on and so forth. And you'll see that you should get an ideal value that comes out pretty close to what you record in the experiment. The next experiment you can do if you want to happens to do with volume and pressure reacting to a change in temperature. And so here, if you have a balloon or a Ziploc bag or any other kind of bag that's airtight that you can inflate, you can do this. Basically, you just fill up the balloon, make some estimate as to what its volume is. Maybe you'll have to make a crude estimate as to what its shape is. You might have to approximate something as a sphere and use 4/3 pi r cubed, or maybe approximate something as a rectangle. Totally depends on what you use. Note the temperatures at play. And again, here's a point. Make sure that we're working in temperatures of Kelvin. Kelvin is always the most suitable temperature scale for physics, just because it goes from something physical, like the 0 point is actually something physical, which is absolute zero when all motion completely stops, whereas the other scales are set on something sort of arbitrary. Like Fahrenheit is the equilibrium temperature of a bath of water, salt, and ice. The Celsius 0 point is the freezing point of water, and so you can see those scales are kind of set arbitrarily. It's nice to use Kelvin because the zero scale is actually like the zero energy. Anyway, you will note the temperatures. You'll put the balloon or bag or whatever you have in the freezer, and you'll wait a while, and then you will calculate how much the volume should change and see how well that maps reality. The next part is working through the simulator problems. So for this, we just have one simulator right here, and then it will ask you a host of questions. And one thing that you'll figure out is some of these things aren't super straightforward. Like, it doesn't give you a really easy way to calculate the particle speed, and so you'll have to get a little bit creative there. Maybe you could time how long it takes for it to go all the way across the box, and then you can make some estimate using trigonometry as to how far it actually traveled. Anyway, I'll show you what that simulation looks like. So in our simulation here, we have we have this vessel that has a pump attached to it. It has a heat source, it has a barometer, and it has a thermometer. And so the first thing you want to do, and you can also choose two types of particle. The blue ones are heavier and the red ones are lighter. And so the first thing you can do is start pumping in here, getting some particles bouncing off the wall, and you can see now that the pressure is actually starting to increase up to 11.7 atm. Oh, but I don't want this in atm. Let's go in kilopascals. Cool. So we're just pumping this thing up. Then you can get it cold. Note what happens to the temperature, note what happens to the pressure, look at how the particles are kind of reacting, they're all slowing way down. And then I'll get this thing hot again so you can kind of see the difference. Nice, now they're moving quite a bit faster. And I actually like to use the light particles just because they move a little bit faster so the changes are more drastic. You can see when we get them cold, they're going to slow down quite a bit, and then get them nice and hot, and they're just going all over the place. Cool. The other things you have here are a measuring tool that you can measure the width of the entire box, or you can drag those sliders, and then we also have a stopwatch. So when you're going to calculate the velocity, things like the ruler and the stopwatch might be pretty nice. There's also a collision counter in case you're interested in that. That's kind of fun to watch, but the numbers get pretty crazy. One cool thing to do is watch the wall collisions when you have it at a really high temperature, and then watch the wall collisions when you have it at a much lower temperature, and you'll see it should kind of behave how you'd expect it to. Okay, well, I think that's most of the things I have to say about this week's lab. One more thing that I'd like to point out is just to remind everybody, I don't want you spending a ton of time on these labs. You know, the in-person lab sessions are 2 hours, and I don't want this to be, much more, if any more of a time commitment than that. So remember, when you're filling out your lab report, once you get to about that 2-hour mark, even if you're not at, the best stopping point, or you're not totally done doing what you were working on, you're totally free to leave a message to me that says, hey Evan, I got to this point, my 2 hours was up, and I got to work on my other stuff, because I totally respect your guys' free time as well. I don't want you to be pouring an infinitum of time into this, Alright, take care.